Hi students, let us continue. We have seen the compound type of DC generators, and we are able to see their connections, long shunt, short shunt, based on how the shunt winding is connected. And we said that if the shunt branch or the shunt winding is connected at a distance from the armature winding, it is called long shunt, we said, as you remember. Here the shunt is at a long distance from the armature, it is called long shunt. But if this shunt comes here near to the armature, it is called short shunt. We said this in our last time. Based on the number of turn of the series winding or shunt winding and the voltage they produce, we classified the compound generator as over compounded, flat compounded, and under compounded. You remember this. When the full load voltage is less than no load voltage, it is called under compounded, we say. And if no load voltage is equal to full load voltage, it is called flat compounded. And if full load voltage is greater than no load voltage, it is called over compounded, we said last time. Now next to this, how this can be realized in a single DC generator, how this operation difference can be realized. That's what I'm going to see. So if we have a generator, for example, of having a long shunt in this case, and if we add a diverter resistance. Diverter resistance is nothing but it is a variable resistance which is connected in parallel with the series winding. The series winding of field winding of the generator, we call it as a diverter resistance. So by having this additional resistor, it is possible to realize all these voltage characteristics in a single generator. How? See this now. If the diverter resistor is adjusted to high value, adjust to larger value, obviously IA, which reach here, if our diverter is very high, almost no current is going through this. Most of the current will come through this. So if we assume that this is not there, this is going to be simple compound resistor. We call it is over compounded type. We call this an over compounded type. Now what will happen if we adjust this very small value? If we make this diverter very small value, now the current which reaches here, it almost flow across this. Almost no current can come across this branch. In such type, it's going to have only this winding with this resistor and this field winding. So such type of operation of a DC generator, we call it is under compounded. It's going to be operated under compounded. What will happen if this and this resistors are the same? If it is the same, equal current flows through this branch. So it is going to be flat compounded. So by this way, we can adjust the operation characteristics of a DC generator. So having said this, let us come to the examples. So let us come to the examples on a shunt, on a compound DC generator. So here 3 examples are there. The first example says that a long shunt compound DC generator supplies a load current of 50 ampere at 500 volts and has an armature, series field and shunt field resistance of 0.05 ohm, 0.03 and 250 ohm respectively. Calculate the generator voltage and the armature current, it says. Now we have to draw the circuit for this. it is a long shunt compound generator. So here I prepared a circuit long shunt, so everything is given. RF, array, RS, this is RA, this is supposed to be RA, RS is given, and V terminal is also given. It is 500 volt is given. So what is requested? It is asking the generator voltage and armature current. So EG is asked, and armature current I is also asked. So from this circuit diagram for our DC generator, we know that EG is going to be VT plus IA RA plus RS. This is the equation what we know. So we know VT, we don't know IA. What is IA? IA is going to be, this is IS or IL, what I can say IA, and this is IF, right? It's falling down, and this is IL. So I is going to be IF plus IL. Sorry, IL is already given here. IF has to be fine. Then IF, our IF is going to be VT divided by RF. So VT is 500. RF is how much? Here it's already given 0.05. Therefore IF is going to be, if you divide this, 2 ampere. Then what is IA? The requested one. IA is the summation of the two. So 2 plus IL. This IF plus IL is 50. Therefore IA is going to be 52 amp. This is one required thing. And second, what is the generator voltage? So generator voltage, let me erase this, generator voltage, or let me have some new blank. So generator voltage EG, it is going to be VT plus IA RA plus RS. So we know VT, it's already given 500 volt, plus IA we calculated is 52. RA is given, how much RA? It is given 0.05 plus, and RS how much it is given? 0.03. Therefore our generator voltage is going to be 4.16 volt. This is a required generator voltage. So we have to attempt in such a manner. And the short shunt compound DC generator delivers this much 100 ampere to the load at 260. Generator has shunt, series, and armature resistance, and calculates the voltage generated in the armature winding, assume 1 volt voltage drop per brush. It's almost the same as the first equation, so you try this by yourself. And the third equation, in a long shunt compound generator, terminal voltage is 230 with when the generator delivers 150 ampere. The generator has shunt field, series field, and a diverter, and the armature resistance of 92.015, 0.3, 0.32 respectively. Determine induced EMF, total power generated, and power delivered to the load. It says total power generated, power delivered to the source. That is what it is requesting or asking. So how do you attempt this? Similar with the previous fashion, we have to draw a circuit for the long shunt first. So may take time anyhow. This is my EG, and I'll have EG. This will going to have a resistance, and coil is there. This is RA, RS, LS, and it's a short, long type, so we'll have, say, type RF is there, LF is there, and we have a terminal voltage VT of 230. It's already given. And what is given additionally? Diverter resistance is there. Diverter resistance. So this diverter resistance, it is going to be connected in parallel with this series winding. So we may add here diverter resistance, R diverter. It is connected like this. Okay. So now three things are requested from this. What is induced EMF and total power generated, power delivered to the load. Now induced EMF, EG, I can say the induced EMF EG is going to be VT plus IA. Now since in a normal long shunt we usually call RA plus RS. Now we have a diverter resistor here, so there is an additional resistor in parallel with RS. So what we are going to do, this going to be in parallel with R diverter. See, that is the only difference, R diverter. So we have to get the parallel combination of this and add with RS and get IA, and we can calculate EG. That is something new here. So RS, if I take this RS in parallel with R diverter, everything is given. So this is going to be RS times R diverter divided by RS plus R diverter. So everything is given here. What is this? 0.015 times, so this is going to be 0.015 times 0.03, it's already given, divided by 0.015 plus 0.03. So this value is going to be 0.01 ohm. See, this is a parallel combination. So put here, I think before going down we have to get IA. What is IA? IA is going to be here IA is there, which is equivalent to IS. Here is I load, and this is IF. So IA is going to be IF plus I load. What is IF? VT by, similar with the previous, VT divided by RS. What is VT? 230 divided by, what is RS? RF. RF is already given 92 plus IL is given direct. How much? 150. 150. So let me erase this. Okay, so this is VT, normally it is there, VT, and IA. Now this IA, this value is how much? It is 92, 230 divided by, it is 2.5 plus 150. Therefore my IA is going to be 152.5 ampere. See, 152.5 ampere. Then back to this equation. Okay, so now I know my VT. Okay, my VT is how much? 230. Sorry, my VT is become 230 given this is, and my IA is already known, 152.5 into RA. How much? My RA, how much is it? RA is going to be 0.032 plus, and this is the whole we calculated. How much is it? 0.01. 0.01. Okay, this much. So generated voltage will be totally how much? 236.4 volts. That is how we should attempt a compound generator having a diverter resistor. Diverter, one thing. This is A. And let us proceed to B. What B is requesting? It is asking total power generated. Total power generated. PA, or power generated, we can say EG IA. We can calculate with this. We know EG, it is 236.4 times IA is how much? 152.5. Therefore total generated power will be around 36.5 kilowatts. That is B. And on C, it is requesting power delivered to the load. Power delivered to the load, PL, is going to be VL times IL. We know the VL means V total, I mean V terminal. So V terminal, I can say VT. How much VT? This is VT. VT means 230 times IL. How much? Is already given, 150, right? 150. Therefore power delivered to the load will be 34.5 kilowatts. That is what requested. Okay, that is what is requested. Therefore we can calculate such type of parameters if we are asked in compound DC generator. That is what I have on this DC compound element. And other point which is remaining under this compound generator is a differential compound DC generator. Of course, I touched this in the previous. What makes it differential? Just the magnetomotive force inside the generator is going to have an effect of subtraction. Means this current is leaving the dot and this is entering the dot, so they have opposite polarity. So the net magnetomotive force will have a differentiation, I mean a difference of the two with armature reaction. Therefore it is called a differential, we said. So the net flux, the net magnetomotive force will be the difference of the two. That's the differential normal. When you see the terminal characteristics of the differential compound DC generator, the sum of the two effects occurs that were presented in the cumulative compound DC generator. It is already there this time, though the effect both act in the same direction. Here, what is the difference? Here is the two effects are there. Now in this case, when I increase, IRS voltage drop increase as well. So this increase tend to cause the terminal voltage to decrease. This is one effect, same as the previous one. As I increase, series field magnetomotive force, this increase too. This also increase. This increase in series field magnetomotive force reduces the net magnetomotive force of the flux. Now it is, since it's a differential, this will get reduced. This reduced means F net will be less. F net will be get reduced means again Vt further reduced. In this case it also get reduced. In this case it further reduced. Due to this, the differential characteristic curve is an immediate collapse. See, immediate collapse. So since both these effects tend to decrease Vt, the voltage drop drastically as the load increases on the generator. A typical terminal characteristics is just shown here. It drastically immediate because in compound this has got plus terminal, so the net flux has an opposite effect on Vt than this. But in our case, in both cases, the Vt is decreasing, so the curve will drastically fall down. Curve will drastically fall down. And voltage control for this type of a generator, both the two controls what we have seen in the previous generator types, whether in separate shunt, series, it holds this by controlling the speed at the same time controlling IF or including RF, a variable RF, it holds. And the application of compound DC generator, if you see their application among various type of DC generator, compound one generator are most widely used because of its compensating properties, because it has both the property of series and shunt. We can get desired terminal voltage by compensating the drop due to armature reaction and ohmic drop in the line. Such generator have various applications. One, cumulative compound one generator are generally used for lighting, power supply, and for heavy power service because of their constant voltage property. They are mainly made over compounded operation mode. And cumulative compound one generators are also used for driving motors, for driving purpose. For small distance operations such as power supply for hotels, office, homes, and lodges, flat compounded generators are generally used. And the differential compound wound generator, because of their large demagnetization armature reaction, are used for arc welding when huge voltage drop and constant currents are required. So this differential, they can be used for arc welding.